This is a Road Widgets review of the .0240 SP. This is a 240 volt split phase inverter that's stackable with battery banks that are lithium based with additional expansion. We're going to go through the tech specs, the notable features of this, the capacity and capability of this device, notable benefits, and just kind of what my opinion of this particular platform will be useful for. This power system here, it's 62 pounds. This is not light. It weighs as much as one of my kids. This has up to 2,400 watt hours of power for each battery. So this section right here with the green light is a battery. This section right here is a green battery. If you look at the sides of this guy, there's these little latches that break off here to take this whole thing and lift this battery off. So you can connect the batteries. You can stack smaller, bigger, however you'd like. We've got a bunch of outlets on here. There's 4 outlets that are 120 volt on the front of this under the 2 split phases of this power. And then we have a larger NEMA plug here for 240 volt. This is the same size of plug that you might have in, say, like an appliance. You could even plug an electric car into that. And then this here is a smaller 240 volt outlet, but it's a different format usually used for generator connectors and things like that. So you can, depending on which cables you have, you can hook it up. It's important to remember that the power that comes out of this is North American split phase. This means that these outlets are 120 volts. These outlets are 120 volts. When you look at the legs of power on these 240 volt outlets, if you measure, there's also 120 volts and 120 volts. So this is normal stuff that happens in anybody's house that you might want to plug into. A lot of RVs, a lot of higher end vehicles that are in North America may also use 240 volts as well. This inverter system also has pretty prominently on the front display screen. This display screen here has a number of display options on it. It's got the amp hours remaining on the battery system. There is a Bluetooth connection for this, so you can connect your phone app to this and get this information on your phone. So if this is tucked away in a cabinet and you don't want to look at the screen here, you can check your phone instead. A lot of inverters have a surge capacity. This means that when you first turn on a device, there's an inrush of current that comes into maybe something that has a magnetic load. This would be like a motor or something of that nature. That load needs additional load capacity to get the things going. So that inrush of current needs to be supplied to safely start devices. So this particular inverter setup has 8,000 watts of overload capacity for 10 seconds. And then after that time has run out, you're really going to be at 4,000 watts at maximum capacity at that point. The actual battery capacity of this is 2,500 watt hours per battery. So if we have 2 batteries in this, we have 5,000 watt hours of battery. These are 24 volt nominal batteries, and they have about 8,000 cycles of recharge capacity. When you're thinking about recharge capacity, that doesn't mean if you got to 75% or 50% battery and you charge it again, that's a full cycle. A full cycle is bringing it all the way down to 0 and all the way back up again. This means that at 8,000 cycles, think about if you had to discharge it every single day fully, you would have 8,000 days before you'd run out the life on these batteries. In addition to the front panel with our primary outlets here for power output, we have a side panel that has some specialty connectors. The first here is the solar input. It has a maximum voltage of 130 volts DC, minimum is 35, and you can set up your solar array in a parallel series configuration to max out the wattage at 2,400 watts for the charge. This MPPT controller is just going to convert that into the charge necessary for the batteries inside of here. One of the features of the DC input here is you can also hook up an output from another solar charge controller to this. So that solar charge controller up to 1,000 watts, you can connect this into this per connector and feed the power back into this. So in addition to the built-in solar charge controller, you could connect an additional one from the outside. Each port is 1,000 watts of capacity, so you can hook up 2,000 watts of maximum solar charge controller, like an auxiliary solar charge controller. So this means that between the two of these, you could have 2 different array banks of solar feeding into this. Down below here is the solar disconnect. So this enables the charger controller to be able to connect. This is a photovoltaic rated breaker. Then we have just reset breakers for the front panels over here on the side. Finally, you got this really large connector, which is an inlet connector to be able to charge this battery bank from shore power. Because this is a 240 volt outlet, you'd have to plug it into a 240 volt source. So for example, a 50 amp RV shore connector for an RV park would plug into this to charge. That will charge this very quickly when you have both legs of power going into this. And then finally on this side is the cross connect for another battery bank. Another stack of batteries would have the same top cap, and then the cables would connect between the two to be able to join the battery stacks together. What I'm going to do next is I'm going to talk about how is this actually kind of assembled. So first of all, you see a bunch of green lights on here. If you wanted to take this apart and look at it, the first thing you want to do is turn it off. So we're going to power the inverter off, and then we're going to power the batteries off. Now I'll just undo the latches on this. So you can see here, these latches, just your kind of standard heavy duty. There's kind of a thunk as I open this. And that's the mating connectors disconnecting inside of it. When I pull this apart, we look, there's these really nice little rubber feet on this and just a simple set of Alden connectors. So this is just a power distribution blank is all it is. I really like the rubber feet because when you set it on something, it doesn't move anywhere, it's on to the next piece. There's literally another handle right here underneath here. So if we take off the battery stack, the next piece of it is an actual battery. So we'll just undo these clips. Now what we're doing is we're disconnecting one of the lithium batteries off of this stack of two. So this is a little bit heavier, I'm expecting, so it does the same thing, just kind of comes apart. So we'll lift off. You'll notice it's also got rubber feet, so we can kind of start to see how this assembles. Now, you'll see that this doesn't have a handle on this part. That's because this is expecting to have something plugged into the top of it. Usually, you don't want these connectors just sort of sticking out. So I'm gonna not take it apart any further than this, but you can kind of see how it's built. I'm gonna use the lighter portion of this to explain. The sheet metal on this is all put together with a bunch of screws. There's no sharp edges. They're going to catch on stuff. I really think this feels a lot like just a piece of pretty just industrial gear that you might have in production systems, or, you know, I've worked in IT. These are kind of feel like the same kind of things you'd find in just any power system in a server rack or a computer rack. To me, I'd be really pleased to see all these handles to be able to pick them up and carry them and make them really portable. Definitely worth its effort in kind of packaging this. The little indentations for the wheel, the rubber feet are really nice. It just makes everything stack in a line. And this also starts to isolate the vibration from everything too. So if you put this back on here, the feet are kind of nesting inside of the holes. So they plug into the plugs. The plugs have a little bit of movement on them. The feet have a little bit of squish to them. So this whole thing is engineered to be very resilient to shock and vibration too. So it's not very fragile feeling at all. It feels very solid. Now I'm going to go ahead and stack it back up. Just kind of lay it on here. So we'll just let it drop into this little hole, and then I'll go ahead and latch these. I'll put my power distribution cap on. I don't even have to put a lot of force, I just sort of tamp it down. And then from there, I turn my batteries back on and turn the main inverter on, and it's back on again. I didn't have to do any configuration or plugging, it just sort of worked when I put it back together. I want to talk about their inverter frequency. Now, if you hadn't heard about that before, it might sound a bit like a, I don't know, maybe a gimmicky thing, but it actually has a huge impact on the way inverters function. Sort of the lower end inverters or smaller inverters are called high frequency inverters. And what they do is they have components inside of there to generate a very high frequency signal that is a waveform in AC, and it vibrates and oscillates those components and turns it into a AC waveform. They're then stepped into the reduced in frequency to make your 60 hertz waveform that you would normally have for an inverter with AC power. The drawback to those things is that they don't have a lot of inertia behind them. And what I mean by that is when you put a load on a high frequency inverter, that load will draw all the power out of all the components inside of the inverter very quickly. And that means that your inrush current load, things that you might need that surge for, just physically can't be there. These use a low frequency approach to inverting, which means that there is an actual giant chunk of metal of steel inside of here, a magnetic transformer. And that big magnetic transformer acts a lot like a flywheel. When you are running power through that transformer, there is inertia inside of that transformer. And when you put that big load on it, it has to discharge the magnetic capacity of that transformer until it unloads. Because you have an array of silicon rectifiers inside of here creating your waveform filling into that transformer, this means that you have a very robust inverter system that can take big hits. It's highly efficient. It's much less likely to have failure due to the lesser number of components. It's just a bigger, beefier setup than it is from the typical smaller inverters. Now, don't get me wrong, there's places for smaller, lighter inverters, but when you're having a primary power system in a vehicle, I think it really does pay really a lot of dividends to have a very robust system like this. It turns out that it's a little heavier, but realistically, it's so much better in all the other aspects to use a low frequency power system. You'll note that the section in the middle here, this is the inverter section, is a little taller than the battery sections, and then there's a cap on the top here for the last bit to interchange to the next set of the battery stacks. The maximum stackable amount of batteries is 11 units of batteries. So that's pretty tall. You think about how tall 11 of these would be. Due to the way it's drawing the power from the battery banks, I'm not sure exactly about the internal architecture of why, but you have to always put the inverter in the middle between your balanced batteries. So if you have 5 batteries, you could put 3 on the bottom and 2 on the top. But ideally you should have 6, 3 and 3. If you wanted to get to the maximum of 11, that's 5 below and 6, or 6 below and 5 above, because you want to try to keep your center of gravity maybe a little lower if possible. With the battery interconnect that goes to the next stack over, you can then sort of reduce your stack height so you're not having the scary, tippy, powerful battery thing and be able to roll things around. It just rolls so good. It's like easy. Anyway, so I wanted to set up a little bit of a test here just to kind of explain what we're seeing and why this system is the way it is. First of all, I talked about surge capacity. And what does that mean? It means the ability to overload beyond its initial capacity to provide power, to not brown out, to not fade out when you turn something on. I happen to have this enormous fan over here to my right that is a 1/2 horsepower motor with a start capacitor in it, and it's basically almost as tall as I am, and it's about this big. It's gigantic. My assistant's going to turn it on when the time comes to be able to show sort of what the waveform looks like. The setup that you're seeing here, I've got an oscilloscope. It's a digital oscilloscope. It's got 2 channels hooked up, and they're literally wired to mains. So you'll note that one test plug is plugged into this side, and the other test plug is plugged into this side. I have the scope itself also powered off of it, as well as the fan. By connecting the scope leads to this system, I'm able to measure the waveform. And when we look at this waveform, you see a yellow and a blue line, and they're in opposition to each other. When you see them cross over, that's the 0-point crossing of the AC waveform. When you see them farthest apart, that's where you would make 240 volts across these 2 waveforms. One waveform is 120 volts, the second one is 240. When you add them both together, it's 240. So if you take power from the hot side of both sides of this inverter, you make the 240 volts for those types of devices. When you only pull power from one side, you get 120 volts. What we're going to see here, when we turn this fan on, is one of these waveforms is going to get jittery, most likely, because it's putting an overload, it's drawing down considerably the power draw for this inverter. This inverter can feed 2,000 watts on each leg, and this is a roughly 1,800 watt motor that's going to be powered during this startup cycle. So if my assistant would be so kind as to flip the fan on, we're going to see what happens here. So what you'll see is during that initial startup, there was a little bit of jittery going on. That means that the frequency of the inverter, when it was under extreme load, was attempting to stay within the frequency lock of this power supply. So Now that we're running, we can see the jitter is moving back and forth a little bit because there's some variations in the power draw of the fan, because you can think about it spinning there and being regulated by speed. This is pretty solid for a motor this size. I would expect that it's not perfect, but it's also 1800 watts of draw on this inverter right now too. And I'm really happy to see the waveform basically perfectly balanced for both legs, with us drawing nearly the maximum load on only one of the legs right now. So for a transformer style low frequency inverter, this looks pretty decent. If my assistant would turn off the fan, and we'll see what happens to the waveform, you'll see that it'll turn a lot more solid. And now that it's not running, it's very rock solid again. So I've gone and robbed something else from the studio here for a minute, and I'm going to go ahead and plug my cell phone charger into this. So let's pick one of the high capacity ports. I have a cell phone that can take quite a few watts of juice when we start it. So I'm going to plug that in, and we're going to plug the charger in and see what happens. So now the phone's charging, and you see really nothing. You saw a slight jitter to the waveform when it started, but very acceptable power waveform. When we turned on that fan, that was really a good indicator of what an air conditioning system might actually look like when we turn it on, because that big motor is kind of representative of a type of a compressor. And say you had a rooftop air conditioner in an RV or something like that. Those things are 120 volts. They can only be up to 20 amps for the circuit, and that's roughly what this big fan over here was drawing. So I think that this is going to be really pretty good. When you have the inverters that don't have the transformer coil inside of them and instead are more of the high frequency style inverters, you're going to see that jitter a lot more because they don't have that inertia to stay balanced and stay centered on both the voltage supply and the frequency supply for these devices. So to recap on this system, the principal usages of this stack is going to be mobile applications. Mobile applications means anything from an RVer or somebody traveling. It could mean, say, mobile production or other technical aspects where you need to have good, clean power. It could be, say, a mobile mechanic. Maybe you have electrical devices that you need to power and run, anything from pumps, fans, or recharge your batteries on and things. Maybe even an air compressor, that kind of stuff could run off of this. The goal of this system is to make it very portable and very easy to set up and break down. And anybody who's looking for a platform that is versatile like this, that you can knock down or build back up again, that you can roll around on the floor and move to a new spot, and you're not necessarily super fixed and super intent on just that one application, I think that's where this really shines at. The idea of the handles and everything just begs to be picked up and moved versus just sitting in one spot for a long time. The other thing that I think, it's not really something we can hold here, but it's very tangible, is the product support that's behind this. So first of all these pieces are pretty solid. They're made out of, in my opinion, of looking at a lot of electronics and a lot of devices, this is built out of some really solid pieces. Everything from the cam latches that hold everything together, to the sheet metal and the way it's stamped, to the types of fans that are in here, to the buttons. To me, it's well integrated into something that just is going to take a beating and keep running. When we talk about support and getting a hold of the company for help on these, they've set up their internal product support in such a way to take that information back from customers and from users who are in the field and not just try to fix it or placate you. They're really trying to actually solve the problem. If you look at the history of the devices they've released, they keep incrementing the capabilities of them over time. They're refining the way they function and the way they're built, and they're taking that feedback from their customer base and putting it into the product. So when you see this, this is not just somebody coming up with the idea out of the blue. This is all the culmination of a lot of feedback from a lot of customers they've got, putting it back into this product. So I just think that that's a really important way to operate when it comes to building these types of systems, because without knowing how they work in the reality of life, you can't really adjust and tweak and tune them to become that. When you visit the website for pointenergy.com, and you go look at their products and you're ready to buy something, you don't have to just push the button and hope for the best. It's not going to show up from a box from overseas. It's going to be shipping from a local distribution in the United States. Before you even go there, you can call them up on the phone and just talk to them. You can say, hey, I want to do this with my RV. I want to do that with my production stuff. I want to do this with maybe construction or whatever. You need to talk to them, and then they're going to be able to say, oh, well, you need 2 batteries of capacity. How long do you want to run it for? These questions, if you're not familiar with the technology behind inverters and batteries and stacking and capacity and stuff like that, they'll ease you into that, so you're going to know what you're buying. The fact that it's assembled in the United States, you have people that put it together here that are going to be able to tell you why it's doing what it's doing and how to solve it if there's problems. I think that means a lot for any kind of product that you're investing in, something like this, to make sure that you're up and running all the time. I really appreciate your time that you spent with me today watching this video. Thanks for watching, and I'll see you in the next one.